Now we're going to talk about infinite geometric series. There is a major difference between infinite arithmetic series and infinite geometric series. If you recall, every infinite arithmetic series diverges. So if you are dealing with an infinite arithmetic series, you can't add them up. Okay? However, if you read the statement in blue, because it's really important, some infinite geometric series diverge, whereas others converge. Meaning, if you have an infinite geometric series at your hand, it may add up, it may converge to some number, okay? It may not. It depends on the geometric series that you're working with. So in example 5, what we're going to do is discover the characteristic used to determine convergence for infinite geometric series. We are going to investigate 4 different geometric series, okay? For each series, we're going to make a conjecture as to whether the series converges or diverges. And if we think that a particular series converges, we're going to try to come up with the number that the series converges to. Okay, so this is just an exploration kind of example. Okay, we're discovering what characteristic a geometric series has to have in order to converge. Okay, all right, let's take a look at the first geometric series here. So in part A, our series is 5 plus 25 plus 125 plus 625 and so on. Okay, so the plus dot 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 means this is an infinite series. We're adding all these numbers up. We want to know if this thing converges, okay, meaning can we add it up to a single number? If it doesn't, it is said to diverge, okay? All right, first of all, let's recognize that this is geometric. Okay, I'm just going to write the terms here. So we've got 5, 25, 125, 625, and this trend continues. Okay, if you look at how you go from one term to the next, to go from 5 to 25, we have to multiply by 5. And then to go from 25 to 125, we also multiply by 5. To go from 125 to 625, we have to multiply by 5 and so on. Okay, so this is indeed a geometric series. Okay, the R value here, the common ratio, is 5 because that's the number we're multiplying by to get from one term to the next. Okay, something that is going to be helpful here, since we're talking about this, being a geometric series, I'm going to try to write it in summation notation. Okay, so if I had to come up with a formula, and it's not necessary here, I just want you to kind of get in the practice of this. If we had to write this in summation notation, okay, our index of summation would start at 1, and we're going to be adding up to the infinitely manyth, I don't know how to say that. You're adding infinitely many terms, okay? So you're going to be adding terms up to infinity, okay? What does the expression look like that we are adding up? Okay, well, here's a little shortcut about how you can write it. We've seen this before from our prior discussion. If you're trying to algebraically write down a geometric sequence or series, it has the format a1 times r raised to the n minus 1 power. Okay, so if you do that here, okay, I is going to be our index of summation. We would use a1, that's the first term, that's going to be 5 times the r value. Okay, the r value is 5, okay, raised to the n minus 1 power. But again, our index of summation here is I, so we're going to use an I instead of an n. Okay, this is how you can write this particular series in summation notation. Okay, if you plugged in some I values, you can see that this does generate the terms of the series accordingly. Okay. All right, so let's talk about whether or not we think this thing converges or diverges. Okay, well, the numbers are getting bigger. Every time we go from one term to the next, we're multiplying by 5. So the numbers are getting bigger. They're all staying positive and they're getting bigger. So every time we add another term, we're just adding some bigger positive number than than what came before. Okay, so it doesn't look like, because we're always adding a bigger number, it doesn't look like we're going to be able to reach a sum. We can't add this up to a single number because we're adding infinitely many terms, and we're going to be adding, numbers that keep getting bigger and bigger. Okay, so I'm going to guess here that this series diverges. I can't add it up. Okay, I'm adding infinitely many terms, and the numbers we are adding are positive, and they keep getting bigger. Okay, once we learn the rule for convergence or divergence of an infinite geometric series, we'll come back and review, uh, from the formula why this guy does indeed diverge. Okay. All right. The next geometric series in part B, we have 1 plus 1/3 plus 1/9 plus 1/27 plus dot dot dot. It keeps following this trend. Okay. All right, first of all, we're going to look at this and try to, realize that it is geometric. So I'm just going to write the terms here. So we've got 1, 1/3, 1/9, 1/27, and so on. Okay. A big difference between this series and the one we just saw is that the numbers are getting smaller. Okay. They are still positive, but they're getting smaller. Okay. So let's realize that this is geometric. To go from 1 to 1/3, I have to multiply by 1/3. Okay, to go from 1/3 to 1/9, I again do 1/3 times 1/3. That's going to give me the 1/9. Okay, to go from 1/9 to 1/27, I multiply 1/9 by 1/3. Okay, 1/9 times 1/3 is going to give me 1/27, and so on. So this is geometric. Okay, to go from one term to the next, we're multiplying by the same number each time. This tells us our common ratio is 1/3. Okay, just to get in practice here, I am going to write it in summation notation. Okay, again, we would be starting with an index of 1, and we're adding infinitely many terms. Okay, so we're going to go out to infinity here. How do we write this down? Okay, again, this is geometric. It's going to fit the bill of the first term times the r value raised to the n minus 1 power, or I minus 1 power here, because our index of summation is I. Okay, so the first term here is 1. The r value is 1/3. Okay, so you could generate the terms of this particular sequence or series using this summation notation. Okay, basically 1/3 raised to the I minus 1 power. That is going to give you, that's the expression here for generating the terms of the sequence or series. Okay, it's just good to be in practice of doing this. Okay, all right, do we think this series converges or diverges? Can we add this up? We're adding infinitely many terms. So just, by the nature of adding infinitely many terms, you kind of think, well, I can't reach a single number. Okay, because I'm adding infinitely many terms. I keep adding and adding and adding. However, the terms are getting smaller here. Okay, every time you add the next number, it's going to be a smaller number. Okay, what's the pattern here? Okay, we've got 1 plus 1/3. 1/9 is the same thing as 1/3 squared. 1/27 is the same thing as 1/3 cubed. The next term would be 1/81, which is 1/3 to the fourth. And this trend is going to continue. Okay, like I said, every time we take on a new number that we're adding, the number is getting smaller and smaller and smaller. Okay, so I'm going to go to my calculator. Okay, let's see what happens here. If I just start playing around with this, okay, and I'm adding these numbers, okay, I'll add a few. So let's see here, like this, because this is the trend. Oops. Okay, so let's keep adding a few terms here just to see. what we think is happening. Let's see here. I'll go to the fifth. Okay, so if I add the first few terms, okay, this is what I get. Okay, but remember, we want to add infinitely many. Okay, so if we keep adding, okay, so let me keep adding terms here. So let me go out a few more terms. Maybe I'll go to 1 over 3 to the 10th. Okay, so give me a minute to punch all this in. All right, so one more term. Let's just see what happens. Okay. Wow, that's not that much difference. Okay, between adding up to, let's see, the first here, the first statement here, I added the first 5 terms, and then in the second statement, I added the first 10 terms. And you can see the difference between the two calculations. There's not much of a difference. Okay, if we keep going, okay, maybe I'll do it one more time. Okay, maybe I'll go up to the 15th term. So give me a second. So I'm just punching these guys in. Oops. All right, so 1 over 3 to the 13th. Okay, now I'm going to add the 14th term. And then lastly, I'll go up to 15 here. 1 over 3 to the 15th. Okay, let's see how this compares. Look what's happening, okay? I keep tacking on more terms, okay? But the terms are getting in smaller and smaller, so their contribution is not very much, okay? It looks like if I keep adding more and more terms that the sum is approaching 1.5, okay? So that's going to be my guess here. I'm guessing that this guy converges to 1.5. Which is the same thing as 3/2. Okay, that's my guess here. Okay, again, once we learn the rule, we will come back and confirm this. Okay, so the key here is yes, you're adding infinitely many terms. However, each future term gets smaller and smaller and smaller and smaller. So eventually the contribution becomes almost negligible. Okay, it doesn't contribute anything to the sum. Okay, at the end of the day. Okay, so it looks like this infinite series will add up to a particular number. So it looks like this guy is converging. All right, let's look at the series in part C. Okay, this one's got alternating signs. Okay, so we're adding infinitely many terms, but you got to think about it this way. I add something positive and then I take away a certain amount. Then I add a positive amount. Then I take away a certain amount. So like you're kind of bouncing around here. Does this converge? Can you add this up to a single number? Okay, let's first recognize that this is geometric. Okay, the terms of this series are as follows: 2, -10, 50, -250, and so on. Okay, so if I go from 2 to -10, I've got to multiply 2 by -5. To go from -10 to 50, I have to multiply by -5. To go from 50 to -250, I've got to multiply by -5. So this is indeed geometric with an R value of -5. Okay. Remember, if your R value is negative, that's what's going to produce the alternating signs. Okay. Let's see here. If we want to write this in summation notation, okay, we would be doing A1 A1 times R raised to the n minus 1 power, okay, or I minus 1 power. So here we could write this as the summation from I equals 1 to infinity. A1 is 2 here. Our R value is -5. We'd be raising that to the I minus 1 power. Okay, so this is what's going to produce, this is the summation notation that would produce this series. Okay. All right, do we think we can add this up to a single number? Well, let's think about it. Let's write out some more terms of the sequence, okay? And then try to add them up to see what we think. Okay, so remember, to go from one term to the next, I've got to multiply by -5. So if I go -250 times -5, my next term in the sequence is going to be 1250. Okay, so make sure that's right. Yeah. Okay, so then I'm going to multiply this by -5. Okay, this will be the next term in the sequence. So -6250, and then multiply by -5 again. I'm just generating, additional terms in the sequence. So 31,250. I'll do one more. And then let's see, multiply this guy by -5. Okay. So -156,250. The numbers are getting bigger and bigger. Let me get rid of the commas here. Like that. Okay, so you can see what's going on here. Okay, if we generate additional terms in the sequence or series here, you can see that the numbers are getting bigger and bigger, but the signs are alternating. So, it doesn't look like we're going to be able to add this up because, first of all, we're going from either a positive number to a negative number. We're just bouncing all over the place because of the we're going between positive terms and negative terms, and the numbers are getting bigger. Okay, if you start adding these guys up, let's see here. If we go if we add up the first 5 terms, okay, so if we have, all right, I'm going to start adding. Okay, so if I do 2 minus 10, and then that's going to give me -8, I add 50, I subtract 250, add 1,250, subtract 6,250, add 31,250, subtract 156,250. You can see that the sums are bouncing all over the place. Okay, so it looks like from our just little investigation here, it looks like this series is going to diverge. We cannot add it up. Okay, again, we will confirm this once we learn the rule. Okay, let's move on to the sum in part D. Okay, and then hopefully we'll have enough information to make a guess here about what's going on. Here, our series is -48, -24, -12, -6, and so on. Okay, so one thing to notice here, every number is negative. Every term of the sequence is negative. We're adding a bunch of negative terms. So if the sequence does converge, it will be to some negative number. Okay. The question is, if we keep subtracting numbers in this manner, can we add this up to a finite number? Okay. Let's do this. Okay. Well, one thing before I do this, notice the numbers are getting smaller. Yes, every time we, subtract a number, it's going to be a smaller number that we're subtracting. Okay, so that might be a clue for you. Okay, I'm going to do this. Okay, I don't want the negative signs to be confusing. So every term is negative, so I'm going to factor out a negative sign. Okay, so this is going to be, take out the negative sign. This will be 48 plus 24 plus 12 plus 6 plus, and so on. Okay, so I'm just yanking the negative sign out. What is left, okay, is going to be, my series. I'll just look at it with positive numbers. Okay, getting rid of that negative sign. Okay, that's just a nuisance I'm getting rid of. To go from 48 to 24, I've got to multiply 48 by 1/2. To go from 24 to 12, I multiply by 1/2. To go from 12 to 6, I multiply by 1/2. Okay, so this is a geometric series. Okay, the R value here is 1/2. If I wanted to write this in summation notation, I'm going to leave the minus sign outside of the summation notation. Okay, and then I'm going to add from I equals 1 to infinity. What does my series look like? Well, I have to take the first term, which would be positive 48 because I already yanked out the negative sign, okay, times the R value raised to the I minus 1 power, okay? So this is how you can quickly write it in summation notation, okay? Again, the question becomes, do we think this thing converges? Okay, can we add it up? Okay, so let's continue to write out terms of the sequence or series here. Okay, so to go from one term to the next, we just need to multiply the prior term by 1/2. So 6 times 1/2 is going to be 3. Okay, 3 times 1/2 is going to be 3/2, which is going to be 1.5. Okay, and then if we add the next term, okay, 1.5 divided by 2, okay, that's going to be 0.75. Okay, so the numbers we're adding are getting smaller and smaller. Okay, divide this by 2, the next number is going to be 0.375. If we keep doing this, okay, we go further and further out in our infinite series. Okay, eventually, since the numbers are getting smaller and smaller, their contributions will be negligible. Okay, so my guess here is that this series is going to converge. Okay, but to what? Okay, well, it's going to converge to some negative number because we've got the negative sign out front. Let's just start adding these numbers and see what we think. Okay, so we've got 48 plus 24 plus 12 plus 6 plus 3 plus 1.5 plus 0.75 plus 0.375. Okay, okay, well, I don't know. What's it going to keep doing? Okay, plus, let's see, 0.375 divided by 2. Let's add another term. Okay, let's add another term. So plus 0.375 divided by 2, this quantity divided by 2. Okay, I'm just tacking on more terms and I'm trying to guess as to what's going on here. Whoops. Let's do this again. Plus 0.375 divided by 2 divided by 2. Okay. I don't know. It looks like maybe my guess here is maybe it's converging to 96. Okay. We'll have to check that out. But again, my guess here, it's going to be negative 96 because it has to be a negative sum. My guess here is that it's converging because as you continue to tack on more numbers, the numbers are getting smaller and smaller, so their contribution will eventually be negligible. Okay? All right, so we've got our best guesses down. Okay? Based on our observations on these 4 series that we looked at, okay? Let's go back and look at the ones that converge, okay, and see what they have in common, and then look at the ones that diverge and see what they have in common, okay? So let's see here. Let's talk about converging first, okay? So we think B converges, okay? So we think B converges to 1.5, okay? Well, look at the R value here. Okay, the R value is 1/3. The other series that we think converges is the one in part D. Okay, look at its R value. Okay, the R values are less than 1. Okay, so we had an R value of 1/3, we had one of 1/2. So the R value is less than 1. The 2 series that we think diverge, okay, so let's look at part A. Okay, its R value is bigger than 1. Okay, same thing in part C. Okay, we think this guy diverges. Okay, its R value, its absolute value is bigger than 1. Okay, the absolute value of 5, that's just, remember, the negative sign is just there for the alternating signs. Okay, so the absolute value here is positive 5, that's bigger than 1. Okay, that is the rule. Okay, if you have an R value whose absolute value is less than 1, that's going to cause your terms to get smaller and smaller as you go along. So eventually your terms will get smaller and smaller, so their contributions to the sum will be negligible. Okay, so for an infinite geometric series, when does one converge? Okay, when the absolute value of R, of the common ratio, okay, is less than 1, we will have convergence. Okay, however, if the absolute value of the common ratio is bigger than 1, the series will diverge. We can't add it up. Okay? In R value, an absolute value of R, if that value is bigger than 1, that's going to cause your terms to get bigger and bigger and bigger and bigger. Okay? So your series will not add up. Okay? So last thing here, how do we compute the sum of a convergent infinite geometric series? Okay? Is there a formula? Well, yes, there is. Okay? So we saw this particular formula. This is the formula we're using when we're adding the first n many terms of a geometric series. Okay? Remember, every finite geometric series will converge, and this is how you can figure out the number that it converges to. So what happens is we can use this particular formula to figure out how an infinite series, what an infinite geometric series is going to converge to. Okay, remember, we just said it looks like an infinite geometric series is converging if the absolute value of R is less than 1. Okay, so the key to hone in on is this term. Okay, remember, if you have an infinite geometric series, that means you're adding more and more terms. So the n value here would be approaching infinity. Okay, you might be adding the first 1,000 terms, or the first 100,000 terms, or the first 1,000,000 terms. Your n value is getting bigger and bigger. So what happens here is you have an R value less than 1. Okay, so you might have an R value like 0.5. Okay, and you're raising that small quantity to a huge number. Okay, maybe your n value's 100,000, for example. Okay, if you look at that on a calculator, if I take 0.5 and I raise it to the 100,000 power, that's an extremely tiny number. Okay, the answer is not 0. Okay, it's essentially 0. Okay, so the calculator just zeroes it out. Okay, so my point is, if you have a geometric series, okay, and the absolute value of R is less than 1, and you're raising that tiny number to some huge number, this becomes 0. Okay, that piece of the puzzle zeroes out, and that tells us to add this up, we're going to be left with this. Okay, in the numerator, it will just be A1 times 1, because that other piece will zero out. In the bottom will be 1 minus R. Okay, this is going to be the formula. Okay, I'm going to go ahead and erase this. This is not going to be for the nth partial sum. This is going to be for the infinite sum. Okay, this is going to be your formula. Okay, so if you have an infinite geometric series where the R value, the absolute value of the absolute value of the common ratio is less than 1, your series will converge, and this is the formula you can use to calculate the number that it converges to. All right, now that I know this formula, okay, I'm going to revisit these 4 series, okay, and quickly go through these again. Okay, the series in part A had an R value of 5. Okay, the absolute value of R here is bigger than 1. Okay, so that means this series will diverge. You cannot add it up. Okay, moving on, the series in part B, we said that the R value, the common ratio, is 1/3. The absolute value of R is less than 1. Okay, that implies convergence here, which we thought so just by playing around on the calculator. Okay, how do you figure out what it converges to? Okay, well, you apply that formula we just came up with. Okay, the infinite partial sum, or summing up the infinite series, that's S infinity. Okay, you get it by doing A1 over 1 minus R. Okay, let's see if we get 1.5 or 3/2 like we thought. Okay, the first term in the sequence or series here is 1. We're going to divide that by 1 minus the R value, which is 1/3. Okay, I'm going to go to my calculator. 1 divided by 1 minus 1/3. Boom, look what I get, 1.5. Okay, so we guessed correctly. Okay, this series does converge to 1.5 or 3/2. Okay, moving on. Okay, in part C, this is where we had the alternating signs. Okay, but don't let the alternating signs get to you. Okay, the R value here was -5. That means the absolute value of R is the absolute value of -5, which is +5. That is bigger than 1. Anytime the absolute value of the common ratio is bigger than 1, that implies divergence. Okay, can't add it up. Okay, and that's exactly what we thought when we investigated this on the calculator. Okay, lastly, we had the series in part D. Okay, all the signs were negative. Okay, so we yanked out the negative sign and we played around on the calculator. We think this guy converges to -6. Okay, again, every time you're subtracting a number, the numbers get smaller and smaller. So here we have an R value of 1/2. Okay, if we pulled out the negative sign. So the absolute value of R here is the absolute value of 1/2. Okay, that's less than 1. So this implies convergence. Okay, if we want to know what this series converges to, apply the formula. Okay, the infinite sum here is going to be a1 over 1 minus r. Okay, so that's going to be the first term here is 48. Okay, and this is again assuming we yanked out the negative sign. Okay, at the end I will just tack on the negative sign out front. Divide that by 1 minus the R value, which is 1/2. Okay, pop it into the calculator. 48 divided by 1 minus 1/2. There you go. Okay, the sum is 96 here. We have to make it negative. Okay, we have to go back because we yanked out the negative sign. Okay, that's what this series converges to. Okay. All right, so I know this was a long exercise, okay, but what you need to realize from this, if you have an infinite geometric series, okay, it may converge, okay? It's going to converge if the absolute value of the common ratio is less than 1, okay? And then to figure out what the series converges to, you need to use this formula. On the other hand, if the absolute value of R is bigger than 1, your series will be divergent.